And I'm happy to welcome tonight Laura Jeannie Newman, who is a consultant, facilitator, and coach with the Critical Thinking Consortium, who has worked with mathematics educators from at all grade levels and in various roles across Canada, the United States, the Caribbean, Middle East, and Europe. She recently retired from the Peel District School Board, and Laura serves in various capacities, including an instructional coordinator, coach, and classroom teacher for over 20 years. Previously, Laura taught both at the University of Toronto and York University for almost a decade. She has presented on a wide range of educational topics and has published or contributed to many educational resources. So we're really thrilled that so many people throughout Ontario, not just Southern Ontario, all throughout Ontario, are here to hear and learn from Laura. So Laura, are you ready to take it away? Laura? Okay, so Laura's just going to sign back out and log back in again. So this happens sometimes with technology. So she'll be right back in. She'll just pop right back in. She was having a couple of issues with her microphone and her speakers before. That was resolved.
Can you hear me? Hello, test, test.
Yeah, I can hear someone speaking. Who is that?
It's Joseph. I just wanted to see if my microphone works.
Yeah, yours is working, so that's great. And it'll be awesome if you want to be able to ask Laura questions. So, Laura, are you okay now? Do you want to test your mic?
Yes. Can you hear me all right?
Perfect. There you go. So I'm handing it over to you now.
Okay. Thank you. Now, it seems like when I've logged back in again, I've lost the capacity to be able to flip through the pages, and I'm not quite sure why.
There you go. There you go, Laura. You have moderator privileges now.
Okay. So I'm still looking. I don't see the arrows where I can actually flip through the pages yet. Should that be showing up momentarily? There we go. Perfect. Thank you very much. Welcome, everyone, and good evening, and thank you for joining us. I'm going to get started right away because we have an hour and a half together, and I'm looking forward to sharing as much as I possibly can with you in each part of this three-part series. And I'm so excited to see so many different people coming from different places right across Ontario. I'm going to start by introducing what we're going to be learning about today. You'll notice that I don't have an agenda. What I have here is a series of questions that are going to be driving your learning today, questions that you're going to be considering, questions that you're going to be thinking about and reflecting on throughout the session today. And our driving question for the day is going to be whether the mathematical processes promote critical thinking and what the relationship is between the two. So you'll notice here that I start with a question, and aligned to that question is a task that we are going to consider, and that's to determine how similar or different thinking critically in mathematics is to thinking within the mathematical processes. You'll notice as well that what I've done is framed a couple of sub-questions that are going to help us actually get to our ability to be able to answer the larger questions, the driving question and the driving task. And those two questions seamlessly feed back into those larger questions and that larger task. And that's the question, what does it mean to think critically in mathematics? And through some investigation in the next hour and a half, I'm going to invite you to determine the essential attributes of critical thinking. And we're also going to be thinking about what type of thinking is required to proficiently apply the mathematical processes. And in order to answer that question, I'm going to be inviting you to describe the mathematical thinking required for the proficient use of the mathematical processes. Now, you'll notice today as I go through a number of the different activities and tasks that I have for you, I'm going to be modeling what I hope you'll be able to understand is important to bring back to the classroom. So when we talk about critical thinking, and often we'll talk about critical inquiry, it has more than just opportunities to invite students to think critically. It's a process that we engage students in. And so at the beginning of that process, you'll see here, I've created what I describe as being a launch. And in this launch, I'm going to ask you to consider each of the 7 mathematical processes. And for those of you who are familiar with them, you'll be able to make very clear, direct connections to them. And for those of you who aren't, I'm just going to ask you to make some general notes for yourself around the following question. What does critical thinking look like and sound like in a mathematics classroom? And this is your starting point. It's what your thoughts are, what you believe critical thinking might look like and sound like. You can consider what your students at your particular grade level, what they might be doing if they engage in critical thinking. And you'll notice here that what I put in brackets, and we'll talk a little bit more about this throughout the session, but what I put in brackets here is quality thinking. Because when we talk about critical thinking, we're actually just not talking about having students surface thinking, but we're looking at when they're engaged in quality thinking. So is their thinking good or not? Having said that, what I'd like to do is give you about 2 minutes, because this is an important part of the process. I'd like to give you about 2 minutes just to do your own individual thinking, your own individual reflection about how you would answer this question. And if you can, connect your thinking to each of the mathematical processes. If you can to some of them, that's great. And if you can't at all, just jot down some ideas, whatever your initial thoughts are about what you believe critical thinking looks like and sounds like in a math classroom. So 2 minutes to do that. And we'll set a timer for you so that you know when the 2 minutes are up. So what you just heard is the timer ringing to say that your 2 minutes are up. We're going to be using the timer throughout our session today. So if when you hear that ding, you'll know that we're going to be continuing, and hopefully you've had enough time to jot down some of your ideas. I want to emphasize the importance at this point of starting in your classroom with your students with a launch and engaging them in their own mathematical thinking right from the very beginning, right from the very start, even before any teaching begins. You'll notice here that I've invited you to think about what your perceptions, your understandings are about critical thinking in a math classroom before we've even started exploring that. And this is important because what I'm going to be doing throughout the session, and you'll see this, is we're going to be revisiting this page, and as we explore some ideas at various parts throughout our session, I'm going to invite you back to this page and ask you if your thinking has been affirmed, revised, or extended. And this is going to allow you to make some connections to your own thinking from the very beginning. Now, this is important because this allows all students, when you do this in the classroom, all students an entry point into the learning process, and it also gives students an opportunity as they go back to this after they've engaged in some learning in the classrooms. It gives them an opportunity to self-correct and self-regulate rather than having the teacher constantly telling them that perhaps they've gotten something wrong or they need to correct something or they need to change their thinking. So this is something that we're doing so that we're going to, I can give you an opportunity to actually experience this because I think the experience is important. And you'll notice what happens by the end of the session as we go back to the pages. We'll talk a little bit about this and we'll talk more about what the impact has been on your own learning of using the launch. We're going to begin now by looking at a number of different examples of critical thinking in a math classroom. And my understanding is, and I'm hoping that many of you who are in this session are teachers who teach students in the grade levels of grades 7 to 10, because most of my examples have been designed to meet the curricular expectations or the content in those courses at those grade levels. I'm starting here because this, I think, is an extremely accessible activity and what I would call an invitation for you to think critically. And in critical thinking language, we call invitations to think critically critical challenges. So you'll hear me talking about the fact that we are now going to engage in another critical challenge, or I'll refer to these tasks as being critical challenges. And in this particular critical challenge, we're looking at, you can see that there's this gentleman here in a black t-shirt, and we've got a girl here who's wearing a red t-shirt, and this is probably a familiar visual to you. It's just, this is actually taken at the CNE, but it happens at many different fairs all over the province and across the country, and actually many different countries. And the question here is, what is the person's most likely age and weight? And you'll see here that what this young lady here is doing is she's trying to guess this gentleman's age within 2 years and guess this gentleman's weight within 3 pounds. And so what I'd like to invite you to do at this point is spend some time just thinking on your own what you think. And I'm going to emphasize something really important, and this is something that we really need to start doing in many of our math classrooms, is instead of asking you what you think the most likely age and weight are, in other words, instead of getting to the answer, what I'd like you to do is focus on the thinking. So what's the nature of the thinking that you would have to do to make a good decision about this person's most likely age and weight? And I'm going to give you a few minutes just to think about that, and then I'm going to share some of the thinking that many students engage in when they try to complete this task. So I'll give you, let's say, 30 seconds just to do some of that thinking on your own. So now that you've had some time to think about what type of thinking you would engage in to complete the task, let me tell you a little bit about what the students would say. And you'll notice again, when this is shared in the classroom with students, we don't immediately get to, so what do you think the most likely age and weight of this individual is? And you'll find that when you start working with critical thinking and math in the classroom, that is what a lot of your students are going to be very tempted to do. Because for many students, their experience in a math classroom has been all about getting to the answer and getting to the answer as quickly as possible. And what we want to do when we engage students in critical thinking in math is actually move away from that and spend some time engaging in some good quality thinking. So what I typically would ask the students is ask them exactly what I asked you. If you could please tell me, what is the nature of the thinking that you engaged in? How would you be able to come up with a good answer? And what did you have to think about? So some of the things the students would say is they would look at this gentleman and they would, in thinking about his age, they would look very closely at all of the evidence in the picture that might give them information about age. And they start to consider all of the evidence in the picture that might help them. So some students might say, well, I'm looking very closely and I'm seeing, is his hair gray? The color of his hair might be something that tells me how old he is. They might also say, well, I want to look at his skin. I want to see what's happened to his skin, and the changes in his skin composition might be telling me give me some indication of his age. Some of the students might talk a little bit about the way he's dressed and the way he presents himself. Other students might talk about the fact that, well, does he have any family members around him? Are there any children? Does it seem like he's married? So what they start to do is they start to identify variables that might actually impact on this individual's age. And they do likewise with the weight. So they start talking about the individual's height, and they start talking about the dimensions of the body and all sorts of different things that are actually quite interesting and quite relevant. But what's important here is they begin with just considering all of the evidence in the picture that they can gather, and evidence that is relevant for them to make a good decision. And then they consider, so how do I use that evidence? What is it that I already know and understand? And the language I give students is, what do you already know and understand to be mathematically true that might be helpful for you to be able to use that evidence in a useful manner. And so students will talk about, they'll talk about gathering the evidence, they'll talk about the knowledge and the mathematical understandings that they already possess, and obviously they take the two and they try to combine the two. And in common language, we talk about that type of thinking as being weighing the evidence. The other thing that students will tend to talk about, and often I'll say to them, so did you immediately come up with a person's age and weight? And students will say, well, no, absolutely not. I started to think about a range, and I started to think about what's not possible and what is possible. So, and then we start, there's the language of plausibility. Looking at this gentleman's age, is it plausible that he's 100 years old or 90 years old? And the students will just chuckle and say, well, no, that's not a plausible response. Okay, so so they talk about how they actually engage in this type of thinking. So I want to ask you very quickly, as a group, were these some of the things that you ended up doing when you were engaging in the thinking? And what were some of the initial, and I'd like to ask them, because this is important, what were some of the initial things that you did? Did you come up with what you thought the answer was? Or did you actually consider all of the evidence first? Or did you consider a range of ages? And I'm going to kind of number those 1, 2, and 3, and I'm going to ask you in the chat box to put your numbers in there just to get a sense. So 1, did you come up with an immediate response, a number? 2, did you think about all the evidence in the picture that would help you decide? And 3, did you think about what background knowledge, mathematical knowledge you already possessed in terms of relationships and ages and ranges and stuff like that? Did you choose that to help you decide? And if you can just show me in the chat box, what did you do? Okay, wonderful. Thank you for sharing. So you can see here, and by the way, this does not surprise me in the least, because I think that all of you are trained and already have the ability to reason mathematically and think critically in the context of mathematics. So if I were to show you what we just talked about, this is all of the thinking that takes place when we consider the question, what is the person's most likely age and weight? And one of the things that I would like to highlight that's really important is you'll notice here that on the board and at the fair, they talk about guess age and weight. Can you guess the weight within so much? Can you guess? And one of the things, and I don't know if this would be true for yourselves as well, and I'd be curious to hear, how many of you use the language of guessing in your math classrooms? Can I just see a check mark if you use the language of guessing in your math classrooms? And if you don't, put an X. Okay, so I'm seeing a number of check marks, some X's. I'm seeing some people say that they would say estimate. So, and what I hear from many teachers, and this is what's really fascinating to me, is I hear teachers say, well, I do use the language of guess, but I actually say, can you make an educated guess, or can you make an informed guess? And the language that we use in our classrooms really, really important, because there is a huge difference between asking students to guess and asking them to do what we're actually asking them to do here, and that's to make an estimate or a conjecture. And here it's an estimate because they're actually looking at a quantitative number, but in mathematics, they don't always translate everything they're doing to numerical form. So we can get students thinking mathematically, and if that's the case, we call this making conjectures. And often what I'd like to talk to math teachers about is the importance that we use the proper vocabulary and introduce students to the proper thinking vocabulary in their classrooms so that they become familiar with this. And I've been doing this work even at lower elementary classrooms, because in lower elementary classrooms we talk about guesses. A lot of the teachers like to talk about guesses as well. But what we're actually inviting the students to do here is not make a guess, and the reason why we tend to say an educated guess or an informed guess is because what we're trying to ask them to do is make a conjecture. And what that means is, in light of the evidence or the information that you're presented with here, even though it's not a full or complete body of information, we'd like you to reason mathematically to come up with what's most likely. And that's very, very different from a guess, because when we ask students to make a guess, what we're asking them to actually do is to tell us absolutely anything, and anything that they're going to say is acceptable, because when we make a guess, there isn't sufficient knowledge, there isn't sufficient evidence or a body of information or knowledge for students to be able to reason mathematically or to reason to come up with a response. So you'll see here that what we have our students doing is making sound conjectures, and you'll notice that when I talk to you about what the students were doing, a lot of this plays out, and what we need to do is make it very explicit for our students that they need to be considering options, in other words, age ranges, weight ranges, possibilities, so that they know enough to be able to say, there are some possibilities that are implausible, there are some that are reasonable, there are some that are more reasonable than others. And so this allows them to actually fine-tune their thinking. And you'll notice down here, their criteria for judging were the things that we talked about they needed to consider as they were trying to make that conjecture. So they had to consider all the evidence in the picture, they had to consider the mathematical knowledge and understanding that they already possess. Typically here it's about the relationships they're going to consider, and then they connect the two. Here's another example of the same type of thinking, having students practicing making sound conjectures, but here the relationships are a little bit more explicit. But notice here, we've also made a little bit more explicit the options. So when I ask the students the second half of my grade 8 school year was most like, I give them various options and give them an option to design their own. But what I wanted to highlight here is the thinking, again, that is taking place and that is repeated no matter in what context you're doing the work around conjecturing, and the connection to reasoning and proving as a mathematical process. So you can see down here that as we get our students making conjectures, they are in fact engaged in the mathematical process of reasoning and proving. They're applying and developing their reasoning skills to make mathematical conjectures, assess their conjectures, and justify their conclusions. And what we've just talked about here is the thinking process that they have to engage in order for them to effectively do that. Here's yet another example, but here in this case, we've expanded the different types of functions that the students would be looking at, but the nature of the thinking remains the same. The students still have to use the same criteria, have to consider all of the different evidence that they're presented with. They have to consider what they already know and understand about the various functions, and they have to connect that in order to choose the best option. So they've got options to consider. So what I'd like to do now is invite you back to the launch sheet, and we've talked a little bit about reasoning and proving, and invite you back to think about what your initial thinking was in terms of what critical thinking looks like and sounds like in the math classroom. And did this example around reasoning and proving, did it affirm your thinking? Are there any new ideas that you would like to add? Were there any aha moments for you? Would you revise your thinking, or would you extend any of your thinking? And I'd like to give you about a minute to do that so that you can go back to what you originally wrote down and add any ideas or thoughts that you have at this time. Okay, again, I'm hoping you had enough time just to go back and consider your thoughts initially. Hopefully there is some affirmation. Hopefully there is some extension in your thinking and some clarity being brought to your thinking. What I'd like to do now is move to a second example. And in this example, we're going to be considering how we move students from sound conjectures to proving. And here's an example that is based on the grade 7 curriculum, and it's quite useful because I've actually used it in grade 9 with my grade 9 students as a review of the relationship between percent, decimals, fractions, and ratios. So what I'd like to do now is offer you some time to actually be thinking about the math, and the critical challenge that the students were asked to engage in was to think about which of the following representations do not belong, and when they decided which does not belong, what needs to be done to make them belong. Now again, this is a practice that is important that we bring back to our classrooms. I'm going to ask you not to simply take a look at all of these and say, well, this is the one I'm going to say doesn't belong and how I would change it, because that's getting right to the answer. But rather, I'd like you to think about what mathematical decisions must the students make to effectively complete this task. What's the nature of the thinking that they have to do to complete the task? And if you want to put your notes in the chat box, that would be great, because I have been reading them, and it's been really nice to see some of your thinking. Okay, so I'm seeing a lot of great ideas being shared. So what I'm going to ask you to do at this point is consider the following decisions, and do they fit with your thinking? If these are the decisions, the mathematical decisions you need to make to effectively complete the task, is there anything missing here? Is there anything that we need to add? Or do these decisions effectively capture all the thinking that the students need to do in order to effectively complete the task? So we can see our one decision is to decide what each representation is showing, interpret the mathematical meaning of the representation. Choose, decide how similar and different sets of representations are. In other words, comparing representations in which show the same mathematical idea, connecting representations. And lastly, decide how to modify the representation to show a different idea to make it fit with the others. Is there anything that you think might be missing here? Okay, so I'm seeing that there's the idea that there's a design element missing, so perhaps there's a way to represent that hasn't been captured. Thank you. I noticed earlier someone had suggested that there needs to be some background knowledge as a starting point for students, and I agree 100% that one of the important ways of actually framing these types of critical challenges for students is to think about the accessibility of all students. Now, what I didn't tell you is where this would be positioned in the learning process. So at this point, the students haven't been taught anything about the relationship between fractions, decimals, percents. They haven't been taught what they've come into the learning process with an understanding of fractions, hopefully a good understanding of fractions, a little bit of an understanding of percents, probably through their experiences, no understanding of decimals yet, and no understanding of ratios. So if you were thinking about your students, where do you think your students would start? Would they start, what type of representation would your students start with? Okay, they'd start with a fractional representation, any particular one, the images. Okay, so for the most part, the pictures, absolutely. For the most part, the students are going to start with things that they are extremely familiar with. So they'll start with perhaps the hundreds grid, or the area, the visual of the fractions that is based on area, the area model. They aren't likely to be starting off with a ruler, which is a little bit more challenging, or the numerical representation, although some students might be able to do that. But what I wanted to highlight was the importance of putting those in there, because what we're doing here is we're actually asking the students to construct their understanding and connect the representations. And often what happens in a math classroom is we teach about fractions, and then we teach about percentages, and we teach about decimals, and we teach about ratios. And then we ask, after all of that teaching and learning, we ask students to make a connection. And what happens here that is very different, you'll notice, is that they're given this right from the get-go, at the very beginning, and they make those connections. They do the thinking. They have to start where, notice how they start where they're still comfortable, but the focus is on the thinking. So every student is engaged in the same type of thinking. Notice the connection between the types of decisions that are necessary in relationship to the mathematical process of representing. Notice that when students are representing, that they're connecting, comparing, selecting, and applying appropriate representations. If we go back to the slide that we previously saw, we saw that they had to interpret, compare, connect, select, and apply. So in one critical challenge, we are getting to all aspects of the process of representing. And notice that this was all designed so that students could determine, and this is through investigation, the relationship among fractions, decimals, percents, and ratios. So I'm going to ask you now again to go back to your launch sheet and considering representing. What thoughts? Is there anything that again has been affirmed? Anything that would revise your thinking? Is there anything that you would extend? Okay, so I'd like to address very quickly, there were some questions here, and I'm really glad to see the thinking. 3 to 5 students prefer Instagram over Twitter, and there was a question about how does that relate to the fraction, and I think the conversation is actually really wonderful, and I think what's really important here is that we want the students. See, what students will typically do is they'll say, well, there's a 3 and there's a 5, so these must definitely mean or say the same thing. And what we want them to be doing is thinking about, do they really mean the same thing? And what happens here is students have an opportunity. Remember my introduction of the idea of the launch. This is where students would begin their learning. And it's not that they would be making the correct connections immediately, but what they would be doing is starting to do the thinking to determine what they think the relationship is across all of these different representations. In the end, what we'd like to see is that the students actually do question the validity of everything on this page, and if everything on this page does or does not fit, and if there are things that don't fit, what do we need to do to change them? If there are things that are misrepresented, going back to selecting and applying the appropriate representations in order to communicate the same mathematical idea is what we're trying to get across here. So I'm really happy to see that there's a lot of conversation about, gee, does the math make sense here? I'm not quite sure. Does everything fit? Well, the design is such that everything is not intended to fit. And sometimes some of the things that students see as being most obvious, and what they tend to do is they tend to arrive at rushed conclusions as opposed to thinking deeply mathematically. We want them to be able to have the time to think through these things. And this might not happen immediately. And this is why, just as I had asked you earlier, what do you think critical thinking looks like and sounds like in the classroom? And I've been asking you to go back to this page and asking you to think, have you affirmed, would you revise or extend your thinking? We want to give students opportunities after they've learned a little bit more to go back to, say, this task and say, is there anything, have I had an aha moment? Did I connect these incorrectly? Would I change any of the connections? We want students to be able to see the value of making mistakes and not necessarily coming up with the one correct answer right away. It's the thinking process, the opportunity to muck about with the thinking, the opportunity to make mistakes and actually learn from mistakes and failure that we really want to start integrating into our classrooms. So this actually would be an example of a great launch for students that they would keep revisiting over and over again until they've sought clarity. Now, one of the things I want to highlight that's very important, and only you would know whether this would fit with your students, this was designed for a particular group of students when I was working with a teacher in a classroom, you have to be thinking about, is this accessible to all of your students? So is there an entry point for all of your students in the classroom? Because we want them to be feeling successful to some degree right away. But we also want this to be challenging enough that they don't solve everything immediately. We want it to be challenging enough for them to say, okay, I'm not familiar with this. I don't know what to do with this. And if I get it wrong the first time, it's not a big deal because I've just learned something in a future lesson that has helped me make sense of this, and I can go back and self-correct. This leads to self-correction and self-regulation, and that's what we really want to see happening in our math classrooms. So I'm hoping that all the questions around these particular representations, I'm hoping that helps to clarify. And if not, please don't hesitate to put some more questions into the chat box. Let's move on to a different example. This was a question that, interestingly enough, we were working with a group of grade 9 students, and this was actually a group of grade 9 students that the teacher was saying, you know, really bright, high-achieving kids. This was a grade 9 academic class, math class, and we realized there was a group of boys, and they were trying to figure out what they were going to do for lunch. And they actually had this experience, and it was fascinating to see it play out. And they had $35, and they're trying to figure out, the three of them, two of the boys, which were top students in the class, they were trying to figure out if $35 was enough for them to go for lunch. And so we decided, based on the experience where we watched them actually struggle with trying to make this decision, we actually created a critical challenge for the students to see if we could really highlight the thinking that they needed to engage in. So in this task, we asked them the question, is $35 enough for lunch for 3? And there was 2 of the boys who were trying to give advice. And we said, so whose advice would you take? If you were the third, would you take Pierre's or John's advice? And this is basically what happened. They stood outside of the classroom and they wanted to go to Urban Burger. They wanted to have grilled cheese sandwiches, and they had $35. And, you know, Pierre, one of the students, says, well, you know, we can share a milkshake. It's way more than enough money. We're fine. And John decides to go online and look up the online menu so he can see the prices and everything, and says, no way, $35 is not going to be able, we won't be able to afford it. We're just going to embarrass ourselves. We can't go. And so we brought this to the students, and we had changed the name of the boys, and we said, so what should they do? Should they take Pierre's advice, John's advice? What should they do? So I want to ask you again, what mathematical decisions need to be made in order for the students to be able to answer this proficiently? And I'll give you, say, a minute to think about this one. If you'd like to put some of your thoughts in the chat box again, that would be great because it's very helpful for me to see as well. So let me ask you, how many of you had an immediate inclination to simply say, well, there's 3 of us, and if I take $35 and I divide it by 3, if I were to answer this question, that would be a good starting point to answer this question. And if you can just put either a question mark, a check mark if you agree, or an X if you disagree, it would be really helpful for me to see. So the check mark is if you started with a useful thought that 35 divided by 3 would be a good place to start. Okay, great, thank you. The reason why I'm asking this is because typically when we ask students this question, one of the first things that they did, and it was really interesting to watch the boys, one of the first things that they did was start thinking about how they were going to actually figure out if they had enough money. So they started off with trying to think of strategies. And what was fascinating to me is the fact that they just jumped right to kind of their procedural algorithmic way of solving things. So when we had the students talk about this, one of the things we asked them to do was we asked them to highlight their thinking. So what would you have to think about in order to answer this question? And when we actually engaged the students in the type of thinking and had them break it down, they said, well, you know, one of the things we have to decide is $35 enough, and who has the better advice? Okay, so that's your decision. Is that your mathematical decision? I don't know, but that's your driving decision. Then they highlighted their options. They said, I could either go with Pierre's advice or John's advice, or some of them said, well, I could come up with my own position on the issue and present my own position on the issue. So they basically came up with 2 or 3 options on how they could present the advice. The part that was really interesting was when we asked them, so how would you decide? How would you decide whose advice to take? And that's when they started to think about, that's when they really started to get to the math that they needed to get to. So they started to talk about, well, we have this criteria, and this is the criteria we need to consider. First of all, if I take the $35, is it going to ensure that all 3 of us can eat a grilled cheese sandwich? Because that's why we all want to go there. And secondly, does the cost fit within our budget? We've got a budget of $35, and we have to consider all the cost considerations. So it's the cost of food, but a number of the students said, well, there's tax, and if you want to leave a tip. And they also then talked about, well, so we have all this information that we can use. And so what we did with the students, we said, okay, so here's your decision, here are your options, here's the criteria you've come up with, and this is all of your evidence. Now mathematically, what do you do? Okay. I'm going to show you in a minute that this is the type of thinking that is really important for students, and that it's layered thinking. This is their starting point. This is what they needed to think about before they actually got to the thinking that they had to do that had them thinking less about the strategy and just using the algorithms, and more about what strategy they were going to use and what algorithms they were going to use and why they would be using them. So thinking, reasoning much more mathematically. Now, what they were doing here is that they were actually engaging in connecting. So they were thinking, so what math concepts and procedures do I need to use to relate this to a particular context that, you know, an everyday context, a particular context that I need to engage in. And we were giving them this question because we wanted them to practice solving problems using proportional reasoning. And there were some specific expectations that were really important for them to get to when they were doing this. What I'm going to do, because it's important that we make a connection, is I'm going to give you a chance to go back to both connecting and the next piece in a moment, because this is what was really critical. The students came up with all these different ways of solving things. They came up with all these different ways of doing what they called the math. And it was fascinating because when we listened to the boys and when we actually brought this to the classroom, most of the students, in fact, I would say at least 90% of the students, sat down and they started to crunch the numbers. They started to do the calculations. They didn't do any of the big picture thinking that they needed to do before they actually got to the number crunching. They just started to crunch numbers. And so when they started to do the number crunching, and I want to ask you what you think, out of each of these strategies, and I'm going to group the strategies. So I'm going to say strategy 1 and 2, you can see that the students did detailed calculations. And remembering, these are grade 9 academic students, so they did detailed calculations using the mathematical evidence that they got from the online menu. Strategy number 3, was using mental math. Which strategy do you think was the most popular in the classroom? Doing detailed calculations or using mental math? So I'm going to say detailed calculations, I'm going to give number 1. Using mental math, number 2, and I'm just going to ask you to show me in the chat box, which do you think was the most popular strategy in the classroom? Do you think that the students tended to respond by starting with detailed calculations, or do you think the students tended to respond by using mental math? So if you think detailed calculations, show me a number 1 in the chat box. If you think using mental math, show me a number 2 in the chat box. And if you're confused, let me know. Put a question in the chat box. Yes, sorry. Was there a question? I wasn't sure if someone was asking a question or not, but I don't see it in the list of participants anymore. So what I wanted to do is just highlight and get a sense of, based on your experience, whether you thought students, really strong students, would tend to jump to detailed calculations or if they would tend to use mental math to solve the question. And what was really interesting is in this particular classroom, the majority of the students started to do the detailed calculations, and they were really quite proficient at it. They did a really good job at doing all the different calculations, but the question here that we wanted them to really answer once they did all of this was to stop and pause and think about, yes, I know that this is doing the detailed calculations and using the algorithms and the procedures is really important, but given the context of the question, you need to be thinking what's the best strategies to use to solve the problem. And this is what really surprised us when we watched the students who were talking about this in the hallway. The fact that they started to actually pull out a calculator and they started to actually figure out, do all of this number crunching, which I think was fabulous that they could do. But from the standpoint and the perspective of mathematical reasoning, actually engaging in mathematics in a useful way, we really wanted them to be thinking about how do you decide what the best strategy is. And so what we had the students do is actually share all the different strategies that they came up with, and then we started to talk about, so how would you judge what is the best way or the best strategy to use to solve the problem? And the students came up, they were really quite good, and they came up with these varying different criteria. And you can see here that what they talked about was, so does it give us what we need to know so that we can make the decision? So is it informative? And one of the things that I talked to them about is, so if it's going to be informative, and I love the fact that they talked about, does it give the appropriate information? Because it goes beyond just accuracy. So I thought it was really neat that they talked about, was it informative? And to be informative, it must be accurate. Was it friendly? Was it easy to use, anytime, anywhere, and easy to understand? And was it efficient? And what was nice about what the students talked about in terms of efficiency wasn't that it was the fastest way to solve the problem, but they really talked about it being a way to solve the problem in the simplest way. It wasn't about speed for them, but it was more about what we really want as mathematicians for our students to be thinking, what is the simplest, most elegant way of presenting a solution? And that's where they got to that's how they got to the efficiency. So they were given these three criteria, and then they went back to all of their strategies. And based on their calculations, and you'll notice that the calculations using the different strategies were their evidence, they chose the best strategy to solve the problem. Now, in the end, it was fascinating because when they went back to the strategy that they chose initially, and we asked them using the criteria for the best strategy, which would you now choose, they really recognized the importance of paying attention to context and the reason why you're doing the math. And for the most part, the students began to say, why were we standing in the hallway trying to do detailed math calculations when what we really should have done was focused on the mental math? And this is why I asked you initially, how many of you started off by just taking 35 divided by 3? Because I think the tendency was for you as proficient mathematical thinkers is you started to think, well, the best way to solve this problem and the best strategy to use if I'm in this situation is to use mental math, not to do all the detailed calculations. So it was a really important aha moment for the students. But what I wanted to do is show the connection to, again, the mathematical process of selecting tools and computational strategies. Because often teachers in the math classroom really pay a lot of attention to computational strategies, and one of the reasons why our students tend to jump to computational strategies right away is because they haven't spent the time to pause and think about what is the thinking that's necessary for me to be able to solve this problem, and how do I choose the most appropriate tools, and how do I choose and decide to apply the most appropriate tools and computational strategies in order to investigate a mathematical idea or solve a problem. So I'm going to invite you now, again, to take 30 seconds, and in this case, thinking about both connecting and selecting tools and strategies, asking you to go back and seeing if your thinking again has been affirmed, if there's anything that you'd want to add, or if there's any way that you'd want to extend your thinking, any ideas that you'd want to write down at this point about what quality or critical thinking looks like and sounds like in a math classroom. Okay, we're going to be looking at two more problems. This one here, I'm going to tell you right away, is going to be focusing on communication, and you'll see this relatively quickly, because what the students were asked to do was to choose the best way to describe something. And I just chose something like, what's the best way to describe going to school? It could be anything that might be interesting in the context of whatever it is that's meaningful and important to them. But typically I would choose something that doesn't have a direct, that students wouldn't see as having a direct connection to math. So for example, what's the best way to describe going to school? What was the best way to describe your experiences this summer? What's the best way to describe how your first term went, or how the first part of your school year went? What's the best way to describe, I don't know if they just had some kind of event at the school, how the event went at your school. These are things students typically wouldn't use mathematics to describe, and that's why I would choose these particular examples. And I would give them some options to consider. So again, notice here, they're invited to make a decision. And here they've got options, and you can use a graph, you can use an equation, you can use words, and there's other ways that you can describe what going to school was like, or any kind of experience was like. And if you have any thoughts about what some of those other ways might be, you can just put them in the chat box. I'll give you a few minutes to think about, again, what would the students have to think about? What considerations would they have to pay attention to as they're deciding what is the best way to describe an experience? And if you have some other ideas about a different form, that would be great too, and you can place those in the chat box. If I could ask, if you're thinking about the students in your classroom, which do you think they would choose as the best way to describe an experience? A graph, words, an equation, or would they choose something else? What would your students do? If you can put your ideas in the chat box, that would be great. What would your students do? Would they choose a graph? Would they choose words, an equation? Would they make another suggestion? And sorry, I'm trying to just take a moment just to scan through the chat box, because it seems as though all of a sudden I just got all your comments that I didn't have sooner. So I apologize for not being able to have a chance to take a look. So I'm seeing they'd say words, a photo essay, pictures, words, words. Some would say a map. Okay, so it's interesting the number of you who have said words, and actually I think that would be a very common experience. I think many students would start off by saying, I think the best way to describe any experience is words. So now let's imagine what would happen if we went through some and offered them some criteria. So what if I offer them the criteria that the best way has to, again, be informative, clearly and accurately describe the details of what it's like to go to school, using appropriate details. It has to be easy to read, follow, and understand, simple and easy to create, and fits the purpose and audience. And now, what happens, and it's fascinating to see what you've said, because what typically happens when I ask students and they begin this task is they always choose the form that is most comfortable to them. And that's the reason why many students choose words, because words are more comfortable to many students. Now let me tell you a bit of an experience of when you work with English language learners. English language learners are the first people to say, I can use a picture. And it's fascinating because they'll say, well, a picture is, if I can use a picture, I can use that picture to describe an experience or going to school. So that's another example or an option that we can offer students as a picture, particularly for English language learners. But now they've got criteria to consider. So they start looking at the criteria and they assess each of these options, the graph, the words, an equation, perhaps a picture, perhaps some of the things that you had suggested. And we talk a little bit about which one would you choose, what's the best way to describe an experience. Now, what's interesting that surfaces around this is the students start saying, well, some of the students start saying, well, words are actually better because words can provide me details about an emotion. Now, the beauty of this type of task with the criteria is now we get some really good discourse in the classroom and we get some debate. Because some students will say, well, words are really good because that there's an emotive element that's going to be missing, that's not going to be there. And then other students will say, yeah, but I can create a variable that defines an emotive element, or I can put an emotive element in a graph and I can still capture the idea that it's there. So students really begin to talk and deconstruct all of these different ways of describing, and then they use criteria to decide what is the best way to describe. Now the criteria is important because the criteria moves them away from what we call preferential decisions. This is my favorite way of doing something. This is the way I like to do things, and moves them towards some more mathematical reasoning. And so here, in the form of communication, and you'll see that when we look at what does it mean to communicate in math, how do I communicate my ideas, how do I know if I'm communicating well in mathematics, they need to understand that they have to have criteria to help them decide. And that criteria actually broadens their perspective that there are a lot of interesting ways to express ideas in mathematics that are actually really, really neat and can capture a lot of the same things like relationships and emotions and a lot of different things without having to write a page of information or a page of text and a page of words. And so all of a sudden students start saying, wow, I can capture the same ideas that I would typically have to write a page in words in one line in the form of an equation, or in half a page in the design of a graph. And so they start to see the real value of mathematics and the different tools of mathematics as a powerful way to communicate. The really important piece here, however, is the use of criteria. Because if they use this criteria, and every time they go to choose a form of communication, they're making a mathematical decision. They are thinking about what is most appropriate. And we look at the actual, when we look at the actual mathematical processes, we're actually thinking about what is most appropriate in the context of what it is that they're trying to communicate. Now that brings us back to our launch sheet once again, but I'm very cognizant of the time, and there are a couple of things that I want to do. So typically I would invite you to give you a little bit more time to do this thinking, but I'm sure that you're doing the thinking as adult learners already. So I want to move to my final example. And in my final example, here's the question. And you'll notice that I'm framing this a little bit differently. I'm going to ask you, which mathematical process do you think plays a more significant role in having the students actually solve this question? And the question is, decide how soon the car will run out of gas. So here, I want you to think, is reflecting as a mathematical process or problem solving as a mathematical process playing a more significant role in helping students answer this question? How soon will the car run out of gas? Now I'm going to give you a few minutes, well, I'll probably give you a minute to read through and look at all the information here, because it'll be difficult for you to decide otherwise. But you'll notice that this is the question that the students are given mathematically. And here the teacher has scaffolded this question with a number of different critical thinking opportunities. So they started by asking the students, which of the following 4 points on this graph help to describe the situation? So we've got 4 points on this graph, and they want the students to be paying attention to the details in the representation and making sure that the students understand the details in the representation before they try to answer the question. So which of the following 4 points help describe the situation? Then the teacher wanted the students to show what would need to change to make the points that don't describe the situation work. So is there anything that you'd need to change here that would create a representation that is more appropriate in describing the situation? And then the question, how do you know your change makes sense? So once you've gone through and you've decided if you're going to change some of these coordinates, some of these coordinate points, how do you know that your changes make sense? And then lastly, is it more likely to take more than 5 minutes to run out of gas, less than 6 minutes to run out of gas, and then to justify their choice? And with a final scaffolding question, what piece of information or assumption must be made clear to help the driver know with precision when the car will run out of gas? So you'll notice here there are several critical thinking invitations that scaffold the thinking for the students. Doesn't tell the students like a typical textbook does, this is what I want you to do, part A, this is what I want you to do, part B, this is what I want you to do, part C, and then get to the answer. It actually walks them through, here's a question that gets you to think about something that's important for you to be able to answer the question. Here's another question that gets you to think about something that's important, that gets you to answer the question. Here's something else, another question I want you to consider. So the thinking is the scaffolding here. There's a focus on thinking. Your job is to decide whether the process of reflection or problem solving plays a more important role in the students being able to effectively solve this problem. So I'm going to give you a few minutes to look at the problem again. Well, not a few minutes because we don't have a few minutes, but let's take about 30 seconds. I'm going to be quiet for 30 seconds and let you read over it, look at the graph. Okay. So you've looked at the question. Just as a reminder, this is right from the ministry document. This is how the process of reflecting is described. This is how the process of problem solving is described. I'm going to give you 30 seconds to read over the descriptions. And I'm going to give you another 30 seconds to think about the mathematical decisions that need to be made to support the proficient application of each of the processes. And this is where those decisions would fall in place in the different scaffolding questions that the students would be asked to respond to. So in the first question, which of the following 4 points on this graph help to describe the situation? The students are verifying. When the students are asked to show what would need to be changed to make the points that don't describe the situation work. Here they're developing, selecting, and applying a variety of problem-solving strategies, but they're also considering viability of alternative approaches. And when they are asked, does your change make sense? They're obviously reflecting and monitoring their thinking by judging the reasonableness of their decisions. And when they justify their choice again, they have to verify their decision again. So I noticed many of you said reflecting, and that's really, really quite impressive, because I have to tell you, so many times when I begin with this question and this task, many teachers actually end up starting off by saying problem solving, because they think that problem solving is the big umbrella mathematical processes that encompasses everything that the students, that encompasses all of the other processes. And one of the things that I think teachers who really focus on mathematical thinking and proficient mathematical thinking in their classrooms begin to realize is the significance of reflecting. And I think that you've done that, and many of you have noticed that. Now, I do want to, there was a couple of questions about, why the points. So just for the math in here, if you ever want to consider using something like this, the students have a number of different options in terms of solving this. They can actually argue that there is points 1 and 3 are related because they show the same rate of change, and points 2 and 4 are related because they show the same rate of change. And so they might argue that they'd want to move point 1 over and point 3 over, or point 2 over and point 4 over, the coordinate points. On the other hand, you might have students that actually say all 4 points work because they just create the first 2 and 4 show the same rate as 1 and 3. Now, what's important here is what we don't do is tell the students, we've already told them that it is a constant rate of 100 drops a minute. So they can verify their thinking by looking at that and considering whether these are actually in the right position. the really powerful piece is when they get into thinking about the different strategies is when we ask them what piece of information or assumption but must be made clear in order for you to precisely answer how soon will this car run out of gas. And the students recognize the significance of the y-intercept as an important piece of information. So that's just a little bit of the math here, but I wanted to show you this just to kind of bring closure to the other two mathematical processes and show you how significant reflecting is as a mathematical process that invites students to think critically. Again, I would invite you back to taking a look at this, and I actually am going to give you 30 seconds to do this because in my closing task for you, I'm going to be asking you to think about what you think the essential attributes or the essential features or elements of critical thinking in math are. So I'd like you to go back. I'm going to give you 30 seconds and reflect on what critical thinking looks like and sounds like in a math classroom. And after that 30 seconds is up, we'll go to the next task. And that task is to bring us to pulling together what it means to think critically in math in relation to the mathematical processes. You'll notice that I've been giving you examples of critical thinking in mathematics, but in the context of the mathematical processes and the thinking that's required to proficiently apply those processes. So now I'd like to ask you, what do you think are the essential attributes or features of critical thinking in math? If you were to choose 4 things, what would they be? And if you can put your ideas in the chat box, that would be great. What 4 features define critical thinking in math? Okay, thank you very much for sharing your ideas. Your ideas are absolutely wonderful. They actually capture a lot of currently starting to do some work on creative thinking in mathematics, and a lot of your ideas, particularly around making the connections and generalizing and all of these ideas you've shared are all really, really central to actually creative thinking in mathematics, which is what we call the Critical Thinking Consortium likes to make reference to creative thinking as being a subset of critical thinking. So you're capturing a lot of the elements. To identify what you may have noticed already, all of those things that you've talked about require that 4 things happen all the time. So you might have noticed as you went through, there were some ideas and features that I kept highlighting every time we looked at a mathematical process, and you might have seen 4 keywords repeating themselves over and over again. The first word is a decision, the second word options, the third word evidence, and the fourth word criteria. And I'm putting them out there in no particular order because the order is not important. What is important is that all 4 of these elements are central to critical thinking in a math question. So you'll notice here, and I'm really glad to see the connection to assessment, because as we assess critical thinking, you'll notice that what I've done here is in black text, I've noted what we call descriptive criteria. So these are things that we have students check off as they're doing it. So I say to the students, you're thinking critically if you've come up with options or you've identified the options that are in the question. You're thinking critically if you're making a judgment, or I say to them, drawing a conclusion or making a decision, a mathematical decision. You're thinking critically when you're using criteria, and you're thinking critically when you're using evidence. But then, if I'm looking for what I need to assess when I assess critical thinking, I want to look for quality thinking. So I want my students to be able to differentiate between implausible and plausible options. So I want them to say, well, this option, I just want to be considering plausible options, not ones that make absolutely no sense in the context. And this is really important in the work in mathematics, because in mathematics, students are always saying things that seem to be coming out of left field without any thought to the reasonableness of their responses. So we want them to be considering plausibility, because plausibility is one way to get into reasonableness. We want them to arrive at sound mathematical judgments. We want them to be reasoned, and for them to be reasoned, they have to apply relevant criteria, and they have to be using the appropriate evidence. So hopefully you've seen all of these different 4 attributes or features come into play within all of the different mathematical processes. And I'm going to leave you and close with the following question and see where you stand. Do the mathematical processes promote critical thinking? And from your point of view, based on your learning from today, how similar or different are thinking critically and thinking within the mathematical processes? And I'm going to ask you to choose one of these. They're not similar at all, somewhat similar, very similar, or one is an example or a subset of the other. So if you can quickly just reflect on this question, and in the chat box, tell me what you think. How similar is critical thinking to the thinking required of the mathematical processes? Are they not similar at all, somewhat similar, very similar, or one is simply a subset of the other? Well, thank you everybody for sharing, and thank you for sharing your response to the last question. It is telling me quite a bit about how much you've learned in the session. I hope you've found it useful. What I've put in here is an example of something we call Euler diagrams, a thinking strategy that we use in mathematics. And the next time we get together, we're going to be looking at thinking strategies and the intellectual tools that help our students become more effective mathematical thinkers. So we'll talk a little bit more about this particular strategy that I put on this last page. It'll be our connecting point. So I wish you all a wonderful evening, a wonderful week, and I look forward to our second section together. Have a wonderful evening, everybody.
Thanks, Laura. That was really great. What I loved about the session is that you have examples there that the participants can take right into their classes tomorrow and change one little thing before as they're posing questions to their students. So as always, thanks everybody for coming to the OTS Connect session. Just a couple of housekeeping things at the end. When you log out of the session, you'll be directed to a survey link, or you can click on the link here that's a hot link right on the whiteboard, or that's in the chat, and that will take you to a feedback survey that provides OTS and Laura and the Ministry of Education with some valuable feedback about the session. You'll have 48 hours in which you can complete that survey, and once that's done, it will direct you to download a certificate of completion and that you can use for your professional portfolios. So that's, we'd really appreciate your assistance in completing that the feedback survey. So again, 3 ways that it can be accessed, actually 4 when you receive the links from the resources from tonight as well. And also we have some other great sessions coming up. I should have maybe added Laura's next session on April 13th as well. It's part 2 of the session tonight. But in the next couple of weeks, there's some great sessions coming up as well, and we hope you will go to the OTF Connect website and register for others as well. So I'm just going to stop the recording, and if you could log out of the room, that would be wonderful, and we'll see you again. And it'll be just great to chat with you for a second, okay, Laura, at the end.